Physics Chapter 20 Theory Video 3. I suppose that you have finished doing these questions, the earlier questions, using P1 V1 equals P2 V2. If you have any questions, please raise them. So now we are going to discuss how change in temperature affects the gas, the volume of the gas, and so obviously we are going to we are still referring to Boyle's law. So in Boyle's law, you can remember that we discussed about maintaining the temperature constant. So that is how Boyle's law keeps the the temperature of the gas is fixed, but the relationship between pressure and volume changes. So if the temperature of the gas is allowed to change, what would happen is what we are going to discuss. So you know that when the temperature is higher, what happens is the kinetic energy of the molecules will be higher. As a result, they start moving faster, which results in the volume, it results in an increase in the volume, right? So so now in this figure 20.6, we can see that the volume of a gas decreasing as its temperature decreases. The opposing detail of what I just explained. Kinetic energy decreases, so it moves in a lesser area or lesser volume. So fixed mass of gas is cooled at constant pressure. The gas will contract, so that its volume will decrease. So then in here, what you have to figure out is, so they have given two lines here. The two lines actually the two lines will give this the two lines here gives you theta in Celsius and T in Kelvin, right? This is volume. So what happens is, when you start at this point, right? So that is positive 120 degrees, like. So you start cooling it down. So as a result, what happens is it reduces, the volume reduces, and then when it reaches 273 degrees, negative 273 degrees, you can see that its volume is volume becomes zero. How is that possible? That becomes possible because at 0 degrees Kelvin or 0 Kelvin, there is no net kinetic energy of the particles. So as a result, they don't collide with anything. So as a result, there is no volume. It cannot have a volume. It doesn't have a pressure. So that means it becomes infinitely small. So this is actually the principle behind the principle behind the Big Bang theory as well. So they say that at the beginning there was something really small. The universe was contained in a very small object. So this object had infinite pressure, and now you know that when you go into miniature scales, our atoms are made up of almost nothing, right? Because there is so much of empty space between electrons and protons. So we are made up of those, almost that empty space. So it is hard for us to understand it, but still theoretically it is something that we need to understand. So in here, what happens is, at 0 Kelvin, it has almost no volume. So that is the theoretical explanation that is given here, right? So then moving on, this graph does not show that the volume of a gas is proportional to its temperature on the Celsius scale, right? It is not proportional to the Celsius scale. if a gas contracted to 0 volume at 0 Celsius, the atmosphere would condense on a cold day and we would have a great deal of difficulty in breathing, right? So if it is, we have to deal with 0 Kelvin, right, not Celsius. However, the graph does show that there is a temperature at which the volume of a gas does in principle shrink to 0, right? So remember the word in principle. Looking at the lower temperature scale on the graph where the temperature are shown in Kelvin, we can see that the temperature is 0 Kelvin, O negative is 273.3 Celsius, right? So this is how the absolute zero principle was developed. So this relationship can be expressed as V, or the volume is directly proportional to T, right? V is proportional to T, that is volume is proportional to T. When the volume decreases, the temperature also decreases. When the volume increases, temperature also increases, and vice versa. So this can be taken as V upon T is constant, and this is also something that you have learnt in O-levels. This is Charles' law, right? So this was developed by the physicist Jacques Charles, and we know that the gas we know that the gas equation is obtained by combining Boyle's law and Charles' law. We take that equation PV equals nRT equation is what we are talking about. So PV divided by T is a constant. So this constant is taken as N, and we will be discussing that later on. But for now, what you need to understand is PV upon T is a constant, right? So for a fixed mass of gas, PV upon T is a constant is another equation that you need to remember. Write down a note. Theoretically, it can be shown that a gas would have zero volume at 0 Kelvin. This relationship applies only to fixed mass of gas at constant pressure. Constant pressure, and is referred to as Charles' law. And then write down V is proportional to T and V upon T is a constant. Underneath that, write, by combining Charles' law with Boyle's law, a single equation for a fixed mass of gas can be obtained. PV upon T equals constant. PV upon T equals constant. So you know what these letters stand for, and you need to know the units as well. So P comes from the Boyle's law, pressure, volume upon T. T has to be in Kelvin, and that is also something that you need to remember. Then we go to real and ideal gases. So we have touched on real and ideal gases in O-levels. So we are going into a little bit of detail here. That is also something that you need to try and understand. The relationship between PV and T that we have considered are based on experimental observations of gases such as air, helium, nitrogen, and so on. So that means these are experimental values, right? In practice, when we have to do this, when we have to actually find the theoretical equivalent, we have to go into extreme conditions, right? So now you probably must have seen that yesterday there was a breakthrough in energy production in the world. So they have figured out a way of extracting nuclear energy by nuclear fusion rather than nuclear fission that is used in the world today. So that fusion, right, is a new principle that has been developed by using the extreme conditions. That is, they have actually tried to prepare a plasma, so that gas under very high temperatures. Like now, for example, we would need 100 million Kelvin temperature on Earth to produce plasma, but they have somehow reached, but at 100 million Kelvin we have nothing that would remain in its natural state. So as a result, we can't actually produce that much of a energy to get that much of heat to produce energy, right? It is not possible. But we can actually we have taken other various methods or theories into good use, and we have the scientists have been able to develop a new way of doing it. So this is also, these relationships were also developed by going into extreme, by doing extreme experiments using extreme conditions, right? So low temperatures or high pressures, etc., we use these things, right? So then the gases will start to deviate from the laws, right? And so that is, they don't behave in the way that that the equations show us, right? Because there would be gas atoms exerting significant electrical forces on each other. So there would be other forces beginning to act, right? So then now here they are going to show us what happens when nitrogen is cooled down towards absolute zero. At first, the graph of volume against temperature follows a good straight line, but when it reaches the absolute zero, it condenses. Condenses means it becomes a liquid, right? Then in the earlier situation, we learned that it applies only to gases at constant pressure. But now when it turns into a liquid, then it obviously deviates from the theoretical behavior. So then ideally it should be a straight line. But in real life, this is what happens. It deviates here, as you can see. Yeah. So this deviation gives us the reality, but this is the straight line, or the broken line gives us the ideal behavior of the gas. I hope you understood this, right? So at 77 Kelvin, it condenses to become liquid nitrogen, and after that, it is no longer valid. So we have to say that it applies to an ideal gas. So the equation would apply to ideal gas. When we deal with real gases, we have to remember that it would be very much different from an ideal gas, right? So we can say an ideal gas is thus one for which we can apply the equation. So if we can apply the equation, then we know that it's an ideal gas. That is, PV upon T is going to be a constant for a fixed mass of gas. But if we cannot use the gas equation, then it is not an ideal gas. Then write down real and ideal gases. The relationship between PV and T is theoretically possible. However, in practice, this might not be the case. Below graph shows what happens to nitrogen when it is cooled down towards absolute zero. Then please pause the video and draw this. After that, write as nitrogen cools up to a certain Kelvin value, it will be a straight line. However, beyond that point, it starts to curve, and by 77 Kelvin, it will condense. And become a liquid. At this point, it deviates from the ideal gas behavior. As a result, we can identify ideal gases separate from real gases by stating that ideal gases obey the following equation, and then write down PV upon T equals constant for a fixed mass of gas. I hope you understood. If you have any questions, please raise them.